Thomson found the charge to mass ratio of these mysterious cathode rays with the cathode ray tube, and from that charge to mass ratio, discovered the electron. That value was so big that we had to have a mass so small, the only possible explanation would be that we had a subatomic particle. Thomson would have loved to find not the charge to mass ratio, but rather the charge and the mass, but he couldn't. Now enter Millikan. Millikan performed an experiment called the oil drop experiment. In that experiment, he had two charged parallel plates. Doesn't really matter how we set the battery up, but the way that I'm drawing it right now, it would make the top plate positive and the bottom plate negative. He injects oil droplets, like tiny little microscopic oil droplets in between these plates. Now, these oil droplets will sometimes be charged. Sometimes they'll be charged because when we inject them with this thing that we call an atomizer is kind of like a perfume dispenser, right? Or a cologne dispenser. You spray it and the particles become really, really small. Not literally atomic size, but really, really small. Sometimes they become charged as they rub against each other or rub against the nozzle of the atomizer. Sometimes we have to charge them by applying ionizing radiation, X-rays to them or something. But you know what? That's not really important for us here today, how they become charged. Okay? Let's just assume that these oil droplets, as they enter these parallel plates, become charged. Some of them positive and some of them negatively charged. The ones that are positively charged will experience two forces acting on them. Anybody want to tell me what one of those forces are? Give me one, Joshua. Good. And gravity is going to act down. In fact, gravity is going to act downwards on both of these particles, whether they're positively charged or negatively charged. Oil droplets, whatever the charge, experience gravity downwards. What other force does that green positive oil drop experience? What other force we got here? Shibo? Yeah, we got an electric force. Kenway, which way is that electric force on the positive green oil droplet? It is downwards. Good. Now, what's going to happen to that positive particle as a result of both of those forces acting downwards? Yep.
It's going to fall faster than normal.
Good. It's going to accelerate downwards. It's going to accelerate downward at a rate greater than 9.81. If it was just gravity, it would go down at 9.81. But because there's a second force contributing to that, it's going to accelerate downward at 12, 14, 18 meters per second squared. All right. Which way is the electric force going to act on this blue negatively charged oil droplet, Chase? Good. It's going to act upwards. Now, we don't know that these two forces are equal. If they're not equal, then this oil drop will accelerate again, just like the first one did. It'll accelerate either upwards or downwards, depending upon which force is bigger. But if those two forces happen to be equal, what's going to happen to this blue one? Can we? It's either going to be suspended or it could move, if it was already moving, at a constant speed. And remember, in physics 20, you guys learned that an object in motion will stay in motion at a constant speed if it's not acted upon by an unbalanced force. So as long as the force is balanced, it'll keep doing what it's doing. It'll stay at rest if it's at rest. It'll stay moving at a constant speed if it's moving. We're going to learn to analyze both situations today, when its particle is suspended / moving at a constant speed and when the particle is accelerating. But what I want to focus on first are those particles that are suspended or moving at a constant speed. In other words, the blue ones. For particles that are suspended, or oil drops that are suspended or moving at a constant speed, we will set Fe equal to Fg. Why am I using Fg here? Remember in the cathode ray tube, we said that Fg was there, but we didn't pay any attention to it. Why do we use Fg here, Logan? Yes. I mean, these oil drops are really, really light, But compared to the mass of an electron that we had in the cathode ray tube, like it's astronomical. The mass is significant, and the force of gravity is significant compared to the other forces involved. So let's set Fe equal to Fg. Notice there's no magnetic force at all here. That means Q times E is equal to M times G. And usually what we do here is rearrange this to solve for Q. We get Mg over E. If we solve for Q, what are we solving for? What variable is Q? Somebody's going to tell me charge. It's charge. Yeah, it is charge. Charge of what? Yep.
The charge of an oil drop.
Good. Not the charge of an electron, but the charge of an oil drop. So why do we want to find the charge of an oil drop? Well, you're going to find the charge of an oil drop once, and then you're going to repeat, and then you're going to repeat and repeat again. Repeat it hundreds of times. Get the charges of hundreds of different oil droplets. What kind of values would we expect to get? Well, we might get 3.2 times 10 to the minus 18 coulombs. We might get 9.6 times 10 to the minus 19 coulombs. These exact numbers not particularly important here, guys. We might get 1.6 times 10 to the minus 17 coulombs. We might get 1.6 times 10 to the minus 19 coulombs. Or 4.8 times 10 to the minus 19 coulombs. What you got to notice here, and what Millikan noticed, is that all of these oil droplets had a charge either equal to this, 1.6 times 10 to the minus 19, or 3 times that, or 100 times that, or 6 times that, or 20 times that. In other words, they all had a charge of 1.6 times 10 to the minus 19, or a whole number multiple of that. That led him to 2 conclusions. First conclusion is that there is an elementary charge. An elementary charge can't get any smaller than that charge. Smallest possible charge. We're going to call it E. And its value is 1.60 times 10 to the minus 19 coulombs. Which, of course, if that's the smallest charge you can have, that's going to correspond, he said, to the charge of an electron. Except that the electron is negative. Millikan found Q over M. Sorry, Thomson found Q over M. Millikan just found the charge. Now, we combine those results, we can find the mass, right? Charge to mass ratio, Thomson. Charge, Millikan. Mass, both. Combine the results of both experiments and get the mass. So the first conclusion here is that we have an elementary charge. We found the charge of an electron. And from that, we can get the mass of the electron. The second conclusion is that charge is quantized. Anybody know what that means, quantized? Money is quantized. Yes, good. Only comes as certain allowed values. Money is quantized, especially in Canada. Can't have 1 cent in Canada anymore, right? We don't have any pennies. You can have 5 cents because we have nickels. You can have 15 cents. You can have $3.15. You can have $1.25. You can't have $1.23 in Canada. We can have an elementary money which is 5 cents, an elementary coin, a nickel, or we can have a whole number multiple of that. We can have 3 nickels, or we can have 17, but we can't have 17 and a half. Money is quantized. Charge is quantized. We can have this value or a whole number multiple of that value. Our first example today is on 763, chapter 15, right? Chapter 15, page 763. It says an oil drop of this mass is suspended. This is good because, quite frankly, this is the only thing that we can deal with right now. We don't know how to deal with it if it's accelerating. We're going to learn that later on. It's suspended in an electric field that's acting downward. How many electrons has the oil drop gained or lost? Well, look, let's set Fe equal to Fg because it's suspended. QE equals m times g because it's suspended. And let's solve for Q. That doesn't give us the number of electrons, but if I get Q, I can from that find the number of electrons. So let's do that right now. Let's find Q. 8.2 times 10 to the negative 15 kilograms times 9.81 divided by 1 times 10 to the 5. And I believe that gives me 8.0 times 10 to the negative 19 coulombs. So that's not what I'm looking for, but I'm close. How do you get the number of electrons from that? We've done this a bunch of times now, right? Yep. Good. We're going to find the number of electrons by taking that value and dividing it by the elementary charge. And I think it works out to be 5. If you get a number that's slightly off, like 5.1 or 4.9, make it 5. Because it has to be a whole number, right? 1 digit, whole number. 1 digit because it's a number. You're not using significant figures here when you're counting. How many people in this room? Well, it's not 27 and a half. It's either 27 or it's 28, right? Hey, we're not quite finished though. Gained or lost? Gained or lost? Please draw a picture. Okay, whenever you're doing one of these problems, and you have directions given to you like this, draw a picture. We have an oil droplet here. We don't know its charge, positive or negative. It's suspended. That means that there must be an electric force up and there must be a gravitational force down. Otherwise, it couldn't be suspended. The forces have to be opposite each other to be suspended. There is an electric field down. Electric field downward. If the force is opposite to the field, what kind of particle does it have to be? Remember, you're either with us or you're against us. If you're against us, then you must be pretty negative, right? Negative particles experience a force opposite to the field. Positive particles experience an electric force with the field. So this is a negative particle, and that means it must have gained 5 electrons to make it negative. If it was a positive particle, it would have lost 5 electrons. All right, I'm going to have you take a look at page 763 for the next couple minutes here. All right, I want to spend a couple of minutes now going over those particles that are accelerating, which could be the particles that had the force upward and the force downward, the two opposing forces, or it could be those particles that have both forces acting downwards. In either case, whether we have forces acting in the same direction or opposing each other, if it accelerates, the forces don't balance each other. Now, what do we do when the forces don't balance each other? Well, first thing we do is draw a Freebody diagram. So if you have a particle like this, we draw that Freebody diagram again. We say the electric force is acting downwards, the gravitational force is acting downwards. If we have a negative particle, we'd say the electric force is upwards, the gravitational force is downwards. Draw that Freebody diagram. And then, if these forces don't balance each other, then we would pull a little physics 20 trick. Think back to about a third of the way through physics 20. When we had multiple forces acting on something, what did we do with that? Yes, F net is equal to the sum of those forces. Fe plus Fg. This one should be Fg, right? F net is equal to Fe plus Fg. Regardless of which direction those forces are in, if they don't balance, if the particle accelerates, F net is equal to Fe plus Fg. Now, do you remember what F net was also equal to besides the sum of the forces? No, not the normal force, no. F net was also equal to
the acceleration.
almost, not the acceleration, but you're close. How about the mass times acceleration? So F is equal to ma, right? So here it's the electric force is Q times E, and the gravitational force is M times G. Now, you got to watch out for signs. Okay, the electric force will be, in this case, the electric force would be negative. So with the gravitational force, in this case, the electric force would be positive. The gravitational force would be negative. But you got to pay attention to those signs, but don't worry about them until you sub numbers in. When you sub numbers in, make the force either positive or negative. Now, you would, in the end, rearrange this to solve for charge. You would get either a value of 1.6 times 10 to the minus 19 or a whole number multiple of that value. Get the same results as we got when it's suspended. Just harder to deal with now. A little bit harder to analyze when it's accelerating. Okay, one example here, and then I'm done with you for the day. 15.4 on 764 says a tiny plastic sphere. So instead of using an oil drop, gentlemen, instead of using an oil drop this time, we're using tiny little plastic spheres. I performed this experiment actually in university with oil drops. And let me tell you, it was the messiest, ugliest, hardest experiment, physics experiment that I've ever performed. Now you often use little plastic spheres or latex spheres, which makes it much, much, much less messy. Regardless, we do it the same way. We have a tiny plastic sphere or an oil drop with this mass. It's placed in an electric field downwards within a vacuum chamber. 10 excess electrons. Is it going to accelerate? And if so, in which direction? If we don't know if it accelerates, we have to assume that it does. Let's calculate A, in fact. If we calculate A and it doesn't accelerate, what value should we get? If we calculate the value of acceleration, but yet we were wrong, it doesn't accelerate, the value of A that we should get is 0. If we calculate A and it works out to be -5, that means it accelerates downward at 5 meters per second squared. So let's do this now. Let's draw a picture. Since we've got multiple forces that don't balance each other, probably don't balance each other, let's draw a picture. We got 10 excess electrons. That means the charge is negative 1.6 times 10 to the minus 18 coulombs. We have an electric field acting downwards. We have a force of gravity acting downwards. Tell me which way the electric force would be on this one. A negative particle experiences a force against the field. The electric force would be upwards. We say F net is equal to the sum of the forces. Uh, 8.2 times 10 to the minus 15 times A equals the charge. We're going to drop the sign of the charge here, right? Because it's, as we always do in an equation. E is 1 times 10 to the 5. Okay, let's solve the right-hand side there on our calculator. Let's say 1.6 times 10 to the minus 18 times 1 times 10 to the 5. Oh, wait. Oh, wait. Oh, what did we almost forget to do? Signs. Yeah, signs. The electric force is positive, so we're okay there. The gravitational force is negative. That was close. So this is what I get for electric force. Let's subtract the gravitational force. 8.2 times 10 to the negative 15 times 9.81 gives me this value. And then let's divide that by the mass, 8.2 times 10 to the negative 15. 9.7. And it is positive. Does it accelerate? Yep. Up or down? Up. The acceleration is positive. It's an upward acceleration. That means that the electric force ends up being bigger than the gravitational force acting down. Yep. No, that's a good question though. No, we don't put the negative in for the electric field because this term is electric force. This term is gravitational force. When we're subbing numbers into an equation like this, it's the direction of the force that we care about, not the sign of the charge, not the direction of the field. Now, the direction of the field will help me with the direction of the force, but we don't sub in negative because the field is negative. We don't sub in negative to gravity because the field is negative. We sub in negative for gravity because the force is negative. Now, here, the field is negative. It is, but the force is positive. So we sub in the sign for the force, not for the field. Does that make sense? That's a perfect transition, that question was, because when we go to the questions that we're going to work on right now on page 764, the answers that are given to you in your textbook are wrong. And the reason they're wrong is because they messed up on the signs here. They messed up on the signs with the field and the force. They said because it's an upward field, oh, let's make it positive. Okay? Well, an upward field with a negative particle would make a downward electric force. Okay? They didn't do that. Make sense? So we're not looking at the fields per se, we're looking at the force, which is, in this case, opposite to the field. So this is wrong, and this is wrong. Okay, let's take a look at those two questions now, please, on page 764.